All right, yeah, let's jump right in. So welcome everyone to getting started building resilient workflows with Temporal's brand new Ruby SDK. We just went to GA last week, so we're really excited to share all about Temporal in Ruby today from our resident experts. A little bit of housekeeping to get started. We'll go over the agenda, so we'll do some quick intros, housekeeping. We'll go into some Temporal basics, talk a little bit about our Ruby SDK, and then why everyone's here, the demo. We get to see it in real time. And if we have time at the end, we'll have our Q&A as well. A little bit of housekeeping. This session is being recorded, and you will be able to receive the recording afterwards, in addition to a PDF of the slides. If you have any questions, please feel free to drop them into the chat or the Q&A kind of tab at the bottom of your Zoom. Throughout the webinar, we'll also hopefully have time for questions at the end. Alex, can you go to the next slide? I just want to make sure I don't miss any of our housekeeping items. Oh, okay. Let's jump into some intros. So we have Tasha Alfano here. She's our staff product manager for developer experience here at Temporal. Yeah, Tasha, want to say hi, introduce yourself?
Absolutely. Thank you so much, everyone who's joining today. It's way easier to not do things than it is to do things. So, you've showed up, you took the first step. That's great. Like Kana mentioned, I get to work on our developer tools, so SDKs, CLIs, all of those fantastic things, which Alex will show you in a second. And we also have some of our fantastic engineers in the chat. So if you see anything that you want to ask a more in-depth question about, throw it in the chat and you may get an answer directly from the author. And Alex, you want to intro yourself too?
Sure thing. My name's Alex Garnett. I am a staff developer advocate at Temporal. I like to work on product launches, trainings, and webinars just like this. I'm really excited about the new Ruby SDK and some of the features that we've brought to that SDK to make it idiomatic and make it integrate nicely with the existing Ruby ecosystem. So I'll be running the demo for you in just a little bit. In the meantime, back to Kana.
Awesome. Hey everyone, my name is Kana. I'm on the product marketing team here at Temporal, focusing on developer experience. So I've been at Temporal about 6 months, and so Ruby SDK has been one of the biggest things that I've worked on so far. Really excited to get it out in the world in GA so everyone can have a go at using it in production and making some cool applications that are resilient and durable. Awesome. So like I said, webinar being recorded. We'll share the recording by email. Use the Zoom Q&A tab or chat for questions. And go ahead, yeah, introduce yourself in the chat. What are you working on lately? Where do you work if you're comfortable sharing, and where you're joining us today. So wonderful. With that, let's jump in. Let's get to the meat of it. Like we said, ask questions. You can also join our community Slack as well and subscribe to our monthly community newsletter, where you can hear all about all the cool new stuff that is coming out from Temporal and how it can help you create more resilient applications. All right. So let's talk about what is Temporal anyway? Let's hear from Alex.
All right, so I'm going to give a platform overview for those of you who are new to Temporal and just help get everyone on the same page. That way you'll understand the features offered by durable execution, as well as how the Ruby SDK fits into the Temporal ecosystem and fits into the ecosystem of Ruby projects that you might already be working on. So, distributed systems in general have a lot of well understood problems and pitfalls. For example, if you're coding a distributed system, you've got to worry about external APIs going down, you've got to worry about databases going offline, or other third-party APIs or endpoints becoming unavailable, or maybe an entire deployment region temporarily getting blown up and losing access to part of your execution environment. Your queues could back up. Whenever I give a temporal booth talk, one of my favorite points to make is that most distributed systems at some point just become queues on top of queues on top of queues. And you become like a raving lunatic looking at like a pinboard chart, just talking about eventual consistency. And that's not that much fun. That's something that you wind up having to re-implement with a different stack every time and just figure out ways of getting to parallelization in a way that doesn't overload whatever you're using for a message broker or for a core queuing function in your application stack. things time out, right? You don't want to have cascading failures where some of your work can't get done. That introduces races or blocking conditions. You don't have good insight into your P95 latency. You're not able to observe one state transition to the next in your application code because maybe what you want to think of as a state transition isn't actually modeled that way internally, and you have to do additional work out of the gate to refactor your system to the point where it can behave in an orderly way, and it can be observed and it can be parallelized because it does behave like a distributed system. You've got to figure out a way of sharing state, maybe with that same queue that you overloaded, that same message broker. You've got to guarantee idempotent transactions for that third-party database integration, and you want to have a guarantee of at least once execution. That way you can be sure all of your processes are definitely being executed in the sequence that you want them to be executed, and you can observe that. You also have to manage some very long running processes. In a lot of distributed systems we talk about, we wind up with certain applications running indefinitely. You might have an orchestrator model where you have some threads that depend on other threads and they all have very complicated inheritance and they all have to have resources allocated to them, right? So if you're running a system that has to run 1,000 or 10,000 or 100,000 instances of the same transaction in parallel, how you're allocating resources to and how you're handling potential collisions between all of those different transactions and parallelizing them gracefully is a non-trivial challenge, especially if you're trying to orchestrate all of this from scratch or using your own tooling. So building these systems can be tough. When you have a distributed system that is not well understood by everybody working on the project, or that does not have effective isolation or compartmentalization, you wind up with decreased feature velocity to shipping. You wind up with systems that are less reliable because it's very hard to get end-to-end visibility into that system, right? If you have a stack that is doing multiple different things, you want to be able to generate observability events from every single one of those steps. And you have to hook in at different places so that way your metrics are actually reliable and robust and trustworthy at scale. You need to have some kind of failover baked in so that in the example I just mentioned, where you have an entire deployment region get blown up, you don't want that to cause catastrophic or cascading issues for the rest of your system. You want things to fail over gracefully, automatically, and hopefully in a way that is invisible to end users so that if you wind up with a tiny little latency blip, that's not a big deal compared to having all of your systems cascade, all your dashboards turn red, you get paged, you don't want to get paged. So you need to handle queuing in a graceful way. Like I said, everything in distributed systems at some point just becomes queuing. Implementing those queues, you wind up with, a soup, in this case, of probably sidekick jobs if you're working with a Ruby stack. Maybe you have Redis. Maybe you're not sure if you're using Redis or RabbitMQ that well. There's a lot of different queuing solutions you might be trying to implement, but at some level, you have to then go in and scale them. You have to scale them horizontally, vertically. That introduces a lot of different concerns. You've got to worry about robustness, retries, and rollbacks when you get into one of those states that has to have some kind of manual intervention or that has to have some recovery performed. And usually you have to build this stack on your own at every job, right? Just because you have Sidekick as a well understood queuing mechanism in the Ruby ecosystem doesn't mean that you have a production scale Sidekick implementation, right? Going from A to B is never trivial, and usually it's that ops layer that is the least trivial of all. Durable execution is Temporal's way of addressing all of these challenges. Durable execution, we say, is crash-proof execution. I like to say that means that your code will never return when you don't expect it to. And so, a runtime error is not cause for you to lose state, to lose variables, to lose a thread. There's no need to constantly persist out to a separate part of your application stack because durable execution means that your code won't return when you don't want it to. Everything that is inherent to a given temporal workflow is automatically durable and automatically persistent. Durable execution is an abstraction that automatically maintains your application state and recovers from failure. If you have one of those runtime errors, whether you've handled it or not, it doesn't mean that your code is automatically just going to return out on you, right? You can have that be stored, you can retry in place, And you can ensure that your application will continue executing despite adverse conditions. If you've got a bug, for example, maybe that issue is with a third-party application that you don't want to have to spend all your time coding around potential edge cases for. Maybe that bug is with your code because you pushed out a bad deployment, and that happens to everybody. Maybe your tests weren't as good as you thought they were, your coverage wasn't perfect. Either way, your application will still persist and wait for you to rescue it with a new deployment or wait for that third-party application to come back up. You don't spend all your time coding defensively around edge cases. You're able to implement the logic that you want and trust that Temporal will handle the rest via durable execution. This improves developer productivity by making applications easier to develop, scale, and support because you get those state transitions monitored. You get all your observability hooks where you want them to, and you get your parallelization out of the box without having to add it after the fact and trying to figure out how to distribute and scale parts of your app. Temporal abstracts away a lot of the complexities around retries, rollbacks, queues, state machines, and timers, because all of that is built in. People will often ask me at conferences, what do I have to do to refactor onto Temporal? And the answer typically is not very much because these are all things you would have to do anyway to be able to achieve parallelization and scale a given application. And so in Temporal, you write code in your choice of programming language using temporal SDKs that are idiomatic to that language. That means that we have lots of nice native calls in all of our SDKs that we support. And it means we can do really cool stuff. Like, for example, if you call sleep in most of our SDKs, rather than just sleeping a thread, that actually schedules a server-side timer. And so it's like, rather than having to figure out a way of implementing schedules, every sleep is almost like a free cron on the server. And a lot of the principles in Temporal work similarly, where you'll take what would be client-side code and you automatically get durable, scalable parallelization that is all tracked on the temporal side, on the server side. You deploy and run your code in your own environment. And so Temporal itself, the orchestrator, that's not what runs your code. You run your code through Temporal workers that you can deploy in pods on your own infrastructure. And you have the ability to scale those workers on your own. And you can also provide any data security or data privacy guarantees that you need from your own infrastructure. Temporal itself, the temporal service, temporal cloud, provides a fault-tolerant durability layer so you can recover from failures because the temporal SDK code is constantly communicating with the temporal service over gRPC. So you might have an architecture that looks like this, one of those famous, everything is queues on top of queues on top of queues architectures that I just talked about. You have to have some kind of orchestrator. Say you have, a order management system that has to perform some kind of payment, inventory, and shipping steps. Something is periodically running to clean up your stuck orders, maybe as a cron job that's trying to go in and garbage collect and rescue orders that have gotten into a weird state. Maybe you have some orders that are in an unrecoverable state because they were able to progress up to a certain point before they hit a non-recoverable error. For example, maybe you took payment and then you verified your inventory was actually out of stock and you have to revert that somehow. So all of a sudden now you're off the golden path. You have to handle all these different flows and you have to send different kinds of messages all across your application stack, maybe through some kind of event-driven architecture to persist all of this to all the different stages that it has to travel to. At some point, this has to get parsed by a front end. Your front end is maybe hitting the same message bus or a different part of your application stack. And you've got to think about all these moving parts and whether every single one of them needs access to the full state of your application at all times in order to make this application flow actually work and to avoid it getting into a non-recoverable or a stuck state due to potential errors that you can't anticipate with any of the different component parts of that application. Can be rough stuff. With Temporal, you can abstract out a lot of that gnarliness sitting in the middle of your application stack. Temporal automatically associates retry policies with each of these activities. So by default, if any of them hit a failure that is unexpected, they'll retry in place until that service is functioning, until you rescue them with a new deploy. If you wind up having to get into a state where you can roll back, you can implement that in temporal just through a series of try catch blocks. So that way, if your execution needs to recover, needs to get into a failed state, it can clean up after itself on the way to doing that. The temporal order workflow itself can be that central component of your execution. That way, you don't need to implement separate queues. All of our SDKs just communicate with the temporal service itself using protobuf over gRPC. So temporal makes a really good central part of your application stack that other aspects, be it your front end or other third-party tools, can integrate with by just implementing temporal clients in their respective language in that stack. So temporal itself handles all that gnarly queuing for you, and it's able to serve as a single source of truth for everything that you put into that workflow execution. This makes your life a lot easier, and it gets you all that parallelism out of the box. Temporal has a few core primitives. For those of you who haven't worked with temporal before, this will be new-ish. So for example, we have temporal workflows. Temporal workflows are the end-to-end steps that your code follows, basically for every transaction, for every customer flow, for every process, you're going to have a temporal workflow. Workflows maintain state. If you have your temporal workflow crash for any reason, your worker goes down, we're just going to keep that workflow waiting for a rescue deployment, for a new worker to start polling. It'll be able to replay the workflow up to the point where it left off and essentially recreate the state exactly as it was. Workflows can sleep through those timers that get persisted server side, and they can receive incoming messages. So you can have a workflow block and wait for input, or you can have it wait for input without blocking, and that input can come from a front end or any other system. Workflows can keep running for years, even surviving infrastructure failures. We have some workflows that model one transaction that's supposed to run to completion, and then that's the end of your workflow. We have some that just persist and keep running. Workflows, you code them yourself, you just write them as you are, and you can even have a Ruby workflow, for example, call a Python or a TypeScript activity. Workflows can fail over, replay, and keep going. Activities are those single units of work that your workflows perform, those state transitions, those external calls that have to talk to a database or some external endpoint or do something on disk. Activities also you implement yourself, exactly as you would without temporal. You just basically decorate them depending on the SDK you're using, and you have a temporal activity. Workflow code generally has to be deterministic, which is to say everything that runs as part of the workflow has to produce the same result each time, but activities do not. So activities, when they interact with external systems, can return the result back to the workflow, and then you can use that input to a subsequent activity. Activities should be idempotent because they can be rerun. We give you a guarantee of at least once execution with activities, and so you can integrate with a third-party database layer to guarantee idempotence and turn that at least once guarantee into an exactly once guarantee through the use of idempotency keys and close coupling. Tasha.
Awesome. Thanks, Alex. So all of that fantastic functionality that Alex just described is now available in Ruby. And that joins our other fully featured SDKs that are available in various languages. Alex, I think we have another slide for that that shows everything. Yeah. So here are all of our languages that we support that have out-of-the-box SDKs and all of the components that come with that. Because you may think, oh, you added a new language. That's not too hard, right? Maybe this SDK is just a wrapper around some APIs. You could feed that into some sort of agent and spit out a new temporal SDK, right? But temporal SDKs are so much more than that. They are the workflows and activities, the APIs that provide those interfaces for you to develop your application, as well as the client for interacting with the temporal service, as well as APIs for managing, configuring, and ultimately scaling your worker processes. And so if you go to the next slide, Alex, our engineers have taken an immense amount of time, as they do with every other SDK that comes out, to ensure that those interfaces, those APIs, and that entire experience is incredibly idiomatic to the language that you're working with. I think my favorite piece of feedback that I hear from temporal users is like, oh, it just felt like writing TypeScript. This just feels like writing Ruby. And so you can see we have one example here, as well as a ton of resources. But Alex is going to show you, the real proof behind Temporal with the demo here, and you can actually see these Ruby interfaces in action. So I'm going to hand it back over to you, Alex.
Sure thing. Before I click through to the next slide, I do want to emphasize a couple of neat things here. So you'll see on the right-hand side, you can install the Temporal Ruby SDK to your project just like any other Ruby gem. Just use gem install temporal IO. We have a landing page for that SDK. All of our SDKs are open source, so you can github.com/temporalio/SDK Ruby, and you can see all of the Temporal Ruby SDK code live right there. Like I mentioned, all of our SDKs just communicate using protobufs over gRPC, and so everything is serialized as it is sent to and from Temporal itself. That way, we're able to cross language boundaries for a lot of our input and error handling, which is really neat. So if you are a Ruby dev and you want to dig into the code, have at it. We have a docs page for our Ruby SDK on docs.temporal.io, so you can see all the content we've created for that Ruby SDK. We also are porting our Temporal courses to Ruby, so you can see the Getting Started with Ruby. Temporal 101 is available in Ruby now. And finally, I think last but not least, we always do a great job publishing different samples, different small patterns for working with Temporal in each new language. So if you go to temporal.io on GitHub/samples-ruby, you can see a lot of the baseline patterns that our SDK team has created to help you understand how Temporal is meant to work within a Ruby application stack. This code example here is really neat. It essentially runs a workflow that does a sleep and then calls one activity. And again, those sleep calls are automatically persisted server side, which is something that I am very proud of and that we always show off at conferences because it just adds like free scheduling to an application that otherwise looks client side. So when you're running temporal applications, we already talked about workflows and activities. There's just a few more component parts to be aware of. Your workers are what actually run your code. Those will load in your workflow and activity definitions, and they'll run in your own infrastructure. Workers can scale horizontally and vertically, so you can have a few worker processes that are constantly polling for work from the temporal service. That way you get that parallelization out of the box. And a temporal worker implementation, I'll show it off in just a second, but it's usually about 25 lines of code to just configure how you want your worker to connect to the service and any other parameters it has to inherit. But the worker is just something that's part of the SDK that you can run out of the box. And then finally, the temporal service itself handles all that persistence, durability, and orchestration. That is what manages the execution of your workflows and activities using task queues. As your app progresses through applications, as it actually runs your workflows and activities, that will persist different events to the service. And that is also where you can use Temporal Cloud in your stack. So Temporal Cloud is a very performant and reliable instance of that temporal service. But we also scale all the way down to running just on your own machine. Our temporal command line client also has a dev server built in that just runs with Go and SQLite on your machine. And so we get really, really small and we get really, really big. And we give you lots of abilities to get started and get running on your own, which I am now going to demonstrate. I've got to do a tiny bit of cleanup here because I was just task switching really quick. So I'm going to switch to sharing my entire screen. Just give me 1 second here. I apologize for the cutover. It's a busy day for yours truly. All right, here we go. Let's get cracking. So here's that temporal web UI. And what I'm doing to run that is just temporal server start dev. Like I said, our command line client contains an entire development server. So you might use the temporal command line client to interact with the server, to query it, to kick off workflows. But if you want to launch an entire dev server, brew install temporal and then temporal server start dev, and you can start developing just like that. Now, if we take a look, I have some sample Ruby application code right here, and I'm going to show off just running a sample temporal application. If we go to our temporal learn website, What I'm going to be following along with for part of this is the code from running your first temporal application with the Ruby SDK. And so for anybody who's curious, you can find this later on at learn.temporal.io and just click through in the sidebar to Ruby and run your first application. So you can find this live on our site anytime you want to see how this demo functions. It's all cloned down from a Git repo. What this does essentially is it's a money transfer workflow that has a few different stubbed out activities. So we're going to say that we have a withdrawal and a deposit taking place. We're not actually doing those steps. If you take a look at the, actually it's a bit too big for me to look at. If you take a look at the activity definition, you'll see this performs some baseline checks, but it's not actually doing anything too in depth. We're just kind of mocking it up. All right. I am going to go ahead and run this workflow. Just give me 1 second here. Okay, and so we have all this definition. This just tells you how to get started. We can scroll through it, and we are then good to go. All right, I am going to go back to here, and here we go. Money transfer. First, I'm going to start one temporal worker. The worker is now running and polling. And now I'm going to kick off the workflow. That is going to run and resolve instantaneously. And so you'll automatically see here on my local temporal dev server, it's been able to run this workflow. It ran this withdrawal and this deposit activity. It had some pre-populated input. It just ran through start to finish. Everything worked the first time. That workflow resolved near instantaneously, and we were all good to go here. You can see here the event history. That progressed through about 17 different state transitions pretty much instantaneously, and we didn't need to observe it because it worked so quickly. What I can do now is I can add a bug to this workflow. We have a divide by zero issue that's going to cause the activity to fail the first time it runs through. I'll go back to my workflows. I'm going to redeploy my worker with the changes. So I now have my buggy worker running. I'm going to kick off a new workflow. And okay, we're seeing some error logging here. And if we click through, we can see this withdrawal activity is failing and it's retrying. Notice our temporal workflows never return when we don't want them to. We have this terminal blocked and waiting for the workflow to return. We have the worker logging out some errors, and you can actually see those errors being returned. You have a stack trace right here actually present on the web UI. So you can see exactly what's going on right now. And we know it's that divide by zero issue. Every time this fails, it's backing off with a slightly longer retry policy, back off coefficient. What we can do is recomment this, say we're rescuing our own deploy, and then redeploy a worker. Notice I'm killing the worker that was actually running this previously. And so you'd think we'd actually lose the state of the workflow execution because the worker that's actually running it went away. Well, not only did we not lose that state because it was able then to resume execution, but the activity was eventually able to complete successfully. What happened there was we saw Temporal's failover capacity in action, which is to say if one worker went away, and that wouldn't necessarily be from a crash or from someone killing the worker manually. It could be because your entire deployment region got blown up and just the worker timed out its communication with the temporal service, and the temporal service assumed the worker was no longer there. Either way, the second a new worker wakes up and begins polling, it's able to rerun the entire workflow execution up to the point that it was previously having an error and then resume execution from there gracefully. In this case, it wasn't a third-party issue, it was an issue with our own code, but Temporal works essentially the same way in either case, where it's going to keep retrying, it's going to save that state, it's going to be able to persist until execution is able to continue, and then with nothing else really apparent to an end user, maybe they'll see a slight hiccup, but it just takes a few seconds of latency typically for a new worker to wake up, begin polling, and be able to complete execution. Pretty neat stuff. We also have here some other temporal workflow code using Ruby. In this case, this is a workflow that can receive input once it's already running. And so we have this workflow that waits to receive some input. It can translate, it can perform some translation functions. And so it's going to change the language that it's waiting to receive input in once it wakes up. There's a few different ways of interacting with the workflow and having them receive input. We have functions called signals, queries, and updates for I/O handling in running workflows. That way, if you kick off a workflow and you want it to wait for input of some kind, it can do that. I'm going to go ahead now and run this one. So I'll get rid of this worker and I'll go over here and I will run a worker from this workflow. And that's going to run all the way through, and it's going to do a bunch of these translation functions right away and then automatically resolve because we've designed this workflow as one of our sample patterns. So it implements everything right out of the start. And so you see right away, it's going to run some activities, receive some input, and so on. It's going to perform some translation by John Q. Approver, which I think is a wonderful name. I am going to legally change my own name to John Q. Approver right after this demo. I did not get the paperwork filed on time. Now, say you don't want it to actually just run all those steps right out of the gate. Say we actually want to comment this out, so we can just have Temporal actually wait for some input ourselves so you can see how that works. Well, one of the things we're waiting on is this approve signal. And so what I've done is I've commented out all that additional I/O. We're just going to start the workflow, and then it's going to wait for input. So you can just see what a temporal workflow waiting for input looks like. So once again now, I am going to rerun my worker and I'm going to kick this off. Okay. And we have a workflow that started. In this case, we had the workflow call just return right away to the terminal. You can have a workflow block or not, and it can return a handle as opposed to results. That way, if you want to dispatch workflows in parallel, they aren't all blocking and waiting. And we're going to send an approve signal to this workflow. Now, normally you'd have a front-end integrate here. You'd have some other application, some other part of your application stack send input to running workflows. In this case, we're just going to go ahead and do this manually, and that way you can see what a front-end call would look like. We're going to send the approve signal with some input. I'm just manually creating some JSON. And here, once again, we were able to complete the workflow because this workflow was just waiting for some input to be able to resolve itself. And that is some Ruby SDK demos. Once again, you can find all of this in the samples Ruby repo from Temporal.io on GitHub, on our Learn site, and in our docs. And I will now jump back to the presentation to wrap us up. Temporal Cloud is our hosted service offering. We are a commercial open source platform. And so all of that nice ops stuff, all of that Temporal at scale, all of those really, really robust queues and our support model is our Temporal Cloud offering. We have lots of exciting logos. We have lots of peers. We have lots of companies that trust Temporal with their infrastructure on Temporal Cloud. And we let them do all their development locally however they want before they are ready to ship on cloud. And so Temporal Cloud is a great way to develop and run temporal applications in production. But if you want to start out just the way I did with that temporal server start dev, that is just fine. You always have access to our local dev server. Temporal Cloud is at feature parity with the Temporal open source server in terms of any and all development features, any and all SDK features. It's just that ops layer that differs for Temporal Cloud. So that is the end of our demo and the scheduled part of our webinar. From here, I'd recommend that you check out the Temporal Code Exchange, where you can see lots of community submitted code samples. We do already have some Ruby projects there, I believe. You can learn more about the Temporal Cloud offering by going to temporal.io/cloud. And you can get started running your Ruby applications on Temporal by going to our Ruby setup guide, which I showed you right here on our Learn site. So back to, whoops, the poll popped up here. Back to our presentation. And we would be very happy for you to join our next webinar, where our SDK engineer, Chad, is going to get into some deeper questions having to do with the Temporal Ruby SDK. So if you're curious about how we integrate with Rails or how we utilize fibers or how you can really work efficiently to provide parallelism in existing Ruby applications, please sign up for that follow-up webinar. That's going to be on November 13th at 9 a.m. Pacific time, 12 p.m. Eastern, just like this one. And at that point, let's handle some questions. Da da da. We have chat. We asked all of our own questions. Those questions are all from us. Does anybody else have any questions they're curious to ask at this point in our webinar?
I think there's one in the Q&A, Alex, if
All
you
right.
can click on that one.
Yeah, I'm on fewer monitors than normal because I am on site today, and I'm going to see if I can discover it. Hang on one second.
No problem.
There it is. All right. Couple questions. Very good. Can we dig in more to the queuing piece? For example, if right now using Sidekick jobs isolated across various queues, do we need to do the same isolation in Temporal via separate task queues? Second, what if we need to throttle because we are overloading a downstream via some call in our activity logic? How could we do that in the temporal world? This is a really great question. So in terms of temporal task queues, we give you task queues as a basic unit of prioritization. When you have one temporal worker, that worker can pull on a specific task queue, and you can give your workers the ability to process certain workflows or certain activities. But not all workers will be able to run all workflows and activities in most production deployments. And you can use those task queues as a way of allocating different resources to different parts of your application stack. And so if you're using Temporal with a Grafana and like with a Prometheus layer, so that way you can actually see that latency and see your P95s and see how long particular work is waiting in a queue to actually get executed, you can allocate different workers, you can further partition your queues, and you can make it so that way you have more resources for some activities than for others. We are also in the middle of adding an additional task queue prioritization feature to Temporal Cloud to give you even more control over that ops layer and over that scalability. If you need to throttle because you are overloading a downstream, that can be handled typically by having a longer backoff coefficient in your activity retry policies. You can also, if you need to, as part of one activity, return a given result, which is how long you should sleep for before calling another activity. And that's a perfectly legitimate pattern. So for example, if you've decomposed a few different external calls into two separate activities. The first one can return a parameter, which is just how long should you sleep before hitting this second part of your stack. Otherwise, using backoff coefficients as part of your retry policy is generally a good way to do it. If you need temporal to treat parts of your stack more lightly, it can do that. Thank you for the good question. The second question, I think I had a second question, and it now just says Coinbase asterisk. Oh, because somebody was able to answer that offline. Wonderful. Yes, the Coinbase temporal gem. There was previously a third-party temporal Ruby SDK. We made some different choices with our official temporal Ruby SDK, and we have some tools and some guidelines for migration available on that SDK's GitHub repo.
Yeah, I'll add just a little bit more to that, Alex. It might say migration guide, but I'll emphasize it's more of a conversion guide. So you won't be really able to migrate running workflows, for example. You can almost think of it like converting from one language to another. That's how different it can be. But this guide can definitely help you out with looking at making that move and converting workloads from an older SDK to a different one.
It looks like that was all the cues for us to A, but we are making the slides available. Thank you for asking. And if there are no other questions, I want to thank everyone for joining here today. Please look forward to our follow-up webinar. And if you have any questions about Temporal or you want to get started, please join our community Slack. please look at our code exchange and welcome to the Temporal community.
Right. Thank you.